Good afternoon. This file contains the pre-lecture slides for class on Tuesday, October 29th. The relevant reading comes from the first two-thirds of the Carey chapter regarding allylic systems and dienes. The takeaways for this pre-lecture include allylic carbons and dienes. Allylic carbons are carbon atoms that are bonded to vinyl carbons. Dienes are any compounds that contain two alkenes. Of the dienes, there are three different types of dienes we'll talk about in the pre-lecture. First is the isolated diene, a compound which has two alkenes with pi orbitals that are independent of one another. Second is a conjugated diene. Here we have a compound with two pi orbitals that are overlapping or are conjugated with each other. Third, we have cumulated dienes. These are dienes in which the two pi bonds in the two alkenes are bonded to the same vinyl carbon. For this pre-lecture, we will focus mainly on the structure of allylic carbons as well as the structure of dienes and talk a bit about their chemical reactivity as related to their structure. So, let's begin by talking about allylic carbons. Allylic carbons are carbon atoms, as we can see here in three different substituents, carbon atoms that are attached to vinyl carbons. So the allyl group is all three of these carbons together, and the allylic carbon is the carbon indicated in red. Notice the vinyl carbons are indicated in black. In some sense, we can think of allyl groups as substituents themselves, in which the allylic carbon is bonded to some other group. Here we have an allylic carbocation, here an allylic radical, and down here a conjugated diene in which the vinyl carbons of one alkene are actually allylic to the vinyl carbons of another alkene. So in order to distinguish between all the carbons, let's just look at this and break it down. Again, the vinyl carbons are indicated in black. These are the carbons that are in the pi bond together. The allylic carbon is the carbon that is bonded to one of the vinyl carbons. It doesn't matter which one of the two it's bonded to. If the carbon is bonded to a vinyl carbon, we say that it is an allylic carbon. When we look at the hydrogens attached to any of these carbons, remember that the vinylic hydrogens are the ones that are attached to the vinyl carbons in the double bond. Therefore, the allylic hydrogens must be the hydrogens that are attached to the allylic carbon. Same thing is true for any substituents. Vinylic substituents are attached to vinyl carbons, and of course, allylic substituents are attached to allylic carbons. Let's take a close look at the allylic carbocation substituent to understand the properties of allylic carbons. So first we begin by looking at the relative rates of ethanolysis of an allylic carbon versus a tertiary carbon. Notice on the left we have the allylic carbon. On the right we have a tertiary carbon. In each case these are chlorides, an allylic chloride and a tertiary chloride. Notice the relative rates of these two compounds when they undergo ethanolysis. The allylic chloride undergoes ethanolysis about 100 times faster than the tertiary chloride does. This should be surprising to you because to this point we have always said that tertiary carbons undergo solvolysis reactions faster than any other types of carbons. What we can see here from the empirical data is that there's some carbons that are faster with regard to their SN1 reactions. Those carbons include allylic carbons. Why is this the case? Well, the faster relative rate of the allylic carbon indicates that the allylic carbocation must be more stable even than a tertiary carbocation, which to this point we thought of as our most stable type of carbocation. There's something about the structure of an allylic carbocation that makes it much more stable than even a tertiary carbocation. Two models are used to explain the relative stability of an allylic carbocation compared to a tertiary carbocation. Those two models include the resonance model and the orbital overlap model. We've talked about both of these models before in the semester with regard to other structure reactivity relationships, so they should be familiar to you here, only applied to a new substituent. So let's take a look at the resonance stability model. Notice that we have an allylic carbocation here, and recall that in any case where we have a charge that's adjacent to a double bond, we can generate resonance structures. As such, allylic carbocations have at least two resonance structures. If we move the pi bond to the carbocation with a mechanistic arrow, we can see we leave behind another allylic carbocation with the formation of a new pi bond. This electron delocalization across three different carbons reduces the energy of the compound and thus increases the stability of the allylic carbocation relative to a tertiary carbocation. In contrast, the orbital overlap model posits that the empty p orbital on the allylic carbocation overlaps together with the filled pi bond on the adjacent vinyl carbons in a hyperconjugation process that allows these two electrons in the pi bond to stabilize the allylic carbocation. This stabilization effect is the same stereoelectronic stabilization effect that we've seen with any type of carbocation. Except in this case, the overlap between the pi orbital and the empty p orbital allows for a much greater stabilization than the hyperconjugation of sigma bonds in alkyl groups on the carbocation. Thus, we can see here as well, we have distributed 2 electrons over the 3 carbon atoms in the allylic substituent, which would lower the relative energy of the substituent compared to a simple tertiary carbocation. Let's look at the impact of the resonance structures of an allylic carbocation on the resultant products in a solvolysis reaction. Here we have a simple substitution reaction in which we're going to replace the chloride leaving group with a hydroxyl group from water. Notice that we get out 85% of one of the products, in this case a tertiary allylic alcohol, as well as a secondary product, a primary allylic alcohol. Notice the difference between the two structures. This carbon in the structure on the left is both tertiary because it's attached to 1, 2, 3 carbons, and it's also allylic because it's attached to a vinyl carbon. Over here on the right, we have a primary allylic carbon. Again, this carbon is attached to only 1 carbon, so that it's primary, but that carbon also happens to be a vinyl carbon, so this carbon here is allylic. In both cases, we have allylic carbons. On the left, we have an allylic tertiary carbon. On the right, an allylic primary carbon. We can do a corollary experiment where we also hydrolyze the chloride from a isomer of our previous structure, replacing again the chloride leaving group with water. You should be able to predict that the resultant products from this reaction are the same resultant products from the reaction on the previous slide with the isomer of this compound. What should be surprising to you, however, is that the relative ratio of products in this reaction is the same as the relative ratio of products we saw on the previous slide. Even though the chloride leaving group is on a primary allylic position, we get more tertiary allylic alcohol as our product than we do primary allylic alcohol. If we look at the resonance structures again of an allylic carbocation, we can see why it's the case that we get more of the tertiary allylic alcohol out than we do the primary allylic alcohol, regardless of which starting material we use. In each case, the resonance structures for both of these compounds are identical to one another. In one case, you have a tertiary allylic carbocation, and in the other case, you have a primary allylic carbocation. Based on what you've learned so far this semester, you should be able to see that this tertiary allylic carbocation is much lower in energy and therefore much more stable than the primary allylic carbocation. As such, in each of these compounds here, when the leaving group leaves, the majority resonance contributor for both of them is the tertiary allylic carbocation, which is more stable. This is because more positive charge is placed on the tertiary carbon, therefore in the end we get more tertiary alcohol in our product regardless of which of the two compounds we begin with. SN2 reactions also occur faster at allylic positions than they do at primary alkyl halides. This too should be surprising to you given that we learned previously that SN2 reactions are fastest at primary alkyl halides. Notice here on this slide the relevant displacement of a chloride ion from a propyl group that is allylic versus a propyl group that is non-allylic is 80 times faster. The reason for this occurs due to 2 different factors. Recall that when you learned about SN2 reactions previously, different factors affected the relative rate of substitution. Those factors included the stability of the leaving group and steric hindrance around the alpha carbon. The second of these two factors, steric hindrance, applies here to allylic carbons in SN2 reactions as well. Notice that the vinyl group coming off of an allylic carbon is trigonal planar, whereas the alkyl group coming off a primary carbon is tetrahedral. The trigonal planar shape of the vinyl group is smaller than the tetrahedral shape of the alkyl group. Thus, nucleophiles are better able to approach the alpha carbon when it's in an allylic position than when it is in a simple alkyl position. The second factor that explains the relatively faster rate of SN2 substitutions at allylic positions has to do with the electronic effect due to the proximal pi bond. Electron delocalization lowers the lowest unoccupied molecular orbital's energy, which means there's lower activation energy for the SN2 reaction to take place. It turns out that free radicals are also stabilized by electron delocalization when they're in allylic positions in the same way that carbocations are. We can draw resonance contributors for allylic radicals in the same way that we can draw resonance contributors for allylic carbocations, producing two different structures that delocalize the radical over three different carbons and thus stabilize the allylic free radical. As such, it's much easier to create allylic radicals than it is to create alkyl radicals due to the fact that electron delocalization weakens the strength of the allylic hydrogen-carbon bond relative to the alkyl hydrogen-carbon bond, as we can see on this slide. The consequence of electron delocalization for allylic radicals is the same as the consequence for electron delocalization of allylic carbocations. Note here on this slide I'm combining together propene together with chlorine, either in the presence of light or not in the presence of light. Remember what you've learned so far. Without the presence of light, we can incur an addition reaction that places the two chlorides across the two vinyl carbons as we see in the top pathway. In the addition of light, chlorine initiates a free radical reaction to substitute at allylic positions. In the case of free radical substitution, we selectively place the chlorine radical at the allylic position due to the two resonance structures contributing to the allylic radical. In any case where you want to selectively place a halogen atom at an allylic position, you should use the compound N-bromosuccinimide to make sure that you do not get any addition reactions with the alkene in an allylic system. Due to the fact that the conjugate base of a deprotonated allylic carbon has resonance structures, we can see that the pKa of allylic carbons is much lower than the pKa of alkyl carbons. This is due to the fact that after deprotonation, we can delocalize the anion over three carbons in two resonance structures in the same way that we could have delocalized either a radical or a carbocation. On this slide, we see the formation of the two different resonance contributors through movement of the lone pair electrons to one of the vinyl carbons by pushing out the pair of electrons in the pi bond to produce the resonance contributor. As before, the charge is delocalized across all three of the carbon atoms, thus stabilizing the conjugate base. Given what we know about the properties of allylic systems, we can inspect the properties of those compounds that include more than one pi bond. For the purposes of this semester, we'll only look at compounds that include two pi bonds in them. These compounds are called dienes because they contain two alkenes. There are three types of dienes you should be familiar with: the isolated diene, the conjugated diene, and the cumulated diene. Notice the difference between each of the structures. In an isolated diene, the two pi bonds are separated from each other by an sp3 hybridized carbon. In a conjugated diene, the two pi bonds are allylic to one another, and in a cumulated diene, the two pi bonds share a vinyl carbon between them. In order to name diene systems, we have to be sure to indicate the relative geometry of each of the alkenes in our naming system. Because there are two alkenes, they can both be either E or Z, so be sure that you name each of them when you give the complete IUPAC name. Notice that E and Z does not apply to cumulated dienes due to the fact that they are linear in structure. can see that conjugated dienes are lower in energy than isolated dienes. To understand this, we have to look at the structure of each of these diene systems to see how it's possible that the same compound with two different isomeric forms can have different energies. Compare the three-dimensional models of the isolated diene and the conjugated diene. Once again, note that in an isolated diene, the two pi bonds are separated by an sp3 hybridized carbon. In a conjugated diene, however, the two pi bonds are allylic to one another, and as such, all four atoms that are in each of the two pi bonds are in the same plane. In this case, our sp3 hybridized carbon is coming off as an alkyl substituent of one of the two alkenes. Because of the relative orientation of each of the pi bonds in an isolated diene and a conjugated diene, we can see that in an isolated diene, the two pi bonds are completely independent of one another as they are separated by an sp3 hybridized carbon. In contrast, a conjugated diene has all of the p orbitals in their pi bonds overlapping with one another. In some sense, this gives us a gigantic pi bond that acts together as a single functional group. Isolated dienes have two separate alkenes that react independently of one another. Conjugated dienes have two pi bonds that are shared together such that they react together as one functional group. Due to the fact that the two pi bonds in the isolated diene are separated by that sp3 hybridized carbon, they're unable to delocalize over all four of the carbon atoms in the same way that they can in the conjugated diene. As such, the conjugated diene, which has more electron delocalization, is more stable. Thus, its heat of hydrogenation is lower. In addition to noting the independent geometry around each of the alkenes in a diene, for conjugated dienes, it's also important to denote the spatial relationships of the two alkenes around the shared sigma bonds between them. To do this, we use the prefixes S-trans and S-cis. The S here stands for the sigma bond that's shared between the two carbons in the two alkenes of the diene. Trans means that each of the alkenes are pointing in opposite directions of the shared sigma bond. S-cis means each of the alkenes are pointing in the same direction on each side of the shared single sigma bond. Notice, regardless of whether the conformation of the diene is S-trans or S-cis, that the p orbitals overlap in both such structures. As such, electron delocalization is equivalent between the two of them. However, it is the case that the S-trans structure is more stable than the S-cis structure. This is simply due to the fact that we have less steric strain in the S-trans structure than we do in the S-cis structure. Notice here the two vinyl carbons coming off of the diene and the S-cis structure approach one another, which creates steric hindrance and thus raises the energy. The last functional group that we'll talk about is the cumulated dienes. Cumulated dienes are even less stable than isolated and conjugated dienes. Again, this is due to the spatial relationship between the two pi bonds that are shared across one vinyl carbon. On this slide, we can see the relative heats of hydrogenation between 1-propene and 1,2-propadiene. Notice that the cumulated diene in this structure has a much higher heat of hydrogenation than the single alkene in 1-propene. The reason for this is because the two terminal carbons in the propadiene structure are orthogonal to one another. The linear structure of the cumulated diene creates a non-planar geometry around the functional group. Both of the terminal carbons are sp2 hybridized, while the internal carbon is sp hybridized. Remember that p orbitals must be combined together to form pi molecular orbitals, and each p orbital is situated 90 degrees away from all of the other p orbitals in the structure. Thus, there is no pi bond overlap between the two alkenes in a cumulated diene. So with that, we conclude our discussion of the structure of the different types of dienes. On Thursday, we will pick up with a discussion of the reactivity of the conjugated diene as a functional group in and of itself. Before we end this pre-lecture, let's just take a second to think about why we would even care about dienes in the first place. On this slide, I've included two different structures, transretinal and cisretinal. Transretinal is synthesized by your body after you consume any fresh fruits and vegetables that contain vitamin A, also known as retinol. The trans structure is converted to the cis structure upon photoactivation of an isomerase in your eye. This change in the geometry of retinal from trans to cis triggers a cascade of chemical reactions that allows retinol to bind to a protein in your eye called opsin. That binding triggers a nerve impulse to your brain, which allows your brain to process the light as vision. This all occurs due to the fact that retinol is a conjugated diene that undergoes a specific spatial transformation. So something as simple as this molecule can help us understand how vision works, and by understanding the chemistry of this molecule, we can correct vision impairments that are related to retinol or retinal production. So with that, this pre-lecture is concluded. As always, be sure to review the relevant readings in Carey and come to class to apply what you've learned.